Hello and welcome to another mini lecture in CS200. Today we'll talk about sorting, which is chapters 19.5 through 19.9 in your Zybook. So let's get started. Sorting is the process of converting a list of elements with something in common into ascending or into descending order. So we specify whether we want it in ascending order, which is kind of the default, but we can also have it in descending order as well. So let's take a look at this participation activity. So if we're given these numbers and we have a time here, what would be your process of trying to sort numbers? It may be by looking at which one is lowest, and then we would swap them in order. So then we would keep going until we got them all in the proper order. You can see my time is 26 for these numbers. However, if you try the same participation activity, you're likely to get different numbers. So what was my process? My process was to start them in looking at the lowest number and swapping those values and continuing and swapping the next lowest and so forth. What we'll do here is we'll look at 4 different sorting algorithms. And we'll talk about their performance based on what we've seen with Big O notation. We're going to begin with selection sort. So what selection sort does is it treats the input as 2 parts, a sorted part and an unsorted part. And it repeatedly selects the proper next value to move on, which is similar to the process I took with that previous example. Let's see it in action, and then we'll go to BlueJ and take a look at the code. Okay, so if I'm given these numbers, we start with the first 2. We call them I and J. I'm not crazy about their designation. It could be like current or next. However, what we want to do is we want to see these numbers and make a comparison. So we know that 9 is not less than 7, and we go to the next one. Is 3 less than 7? So we keep going, and we find that 3 is less than 7. So the next line of code, which you can't see on the screen, is to swap those. And now we update our pointer to start with 9. And essentially what we do is we go through the same process. Okay, if we find a number that's less than there, we move it to our temporary buffer. We have to have a place to move it. And then we move it and change the position with what we found in the second position and then the smallest number. We keep doing this until we get them all sorted. So we're making comparisons, which in terms of time is pretty costly if we have to do that. The first time through, we're making comparisons against, in this case, 4 other numbers. Then when we get the first number in place, and it goes to 3, then 2, then 1. So you can see it can be quite expensive if we have a lot of numbers. So let's take a look at the code. I'm going to open up BlueJ because I think that's a little better. What we have is a selection sort. They have I and J as their values. They also have a temporary place to put the swap value when they're making the change. And then index smallest, which points to the smallest one that was found along the way. They begin with a for loop, and they set I equal to 0. Then you want to go through all the numbers minus 1. So because we're starting with 0, and if the length is 5, we want to go through 0 through 4. Then we increment I at the end of the loop. So what we're doing is we're looping through in a nested loop with J. So J starts with I plus 1. So remember, we have in the first situation, we have the first value to the very far left. So we want to compare it against all the remaining values. And that goes till the end of the array. And then if number sub j, meaning the one that we find, is less than the smallest one that we found so far, then we're going to set index smallest equal to j. So if we find it, once we're done with a loop, we're going to come up with index smallest, and then we're going to have number sub I, which is this value that we're currently on, and then numbers with the index smallest is the smallest one we found. This is the process of swapping it. We need a temporary storage space to keep the value just for the process of swapping. Here's the values. This is our tester. And you can see here we have these numbers that we start with. And what we're going to do is we have our unsorted array, which we're going to print out. Then we're going to call this method with this array of numbers. And then we're going to sort it. So let's go ahead and compile, close this. Let's go ahead and run it. So we have this set of values, and it was quick because there's not a lot of numbers, but you can see it sorted it in the correct order. Looking at the Big O notation for selection sort, we can see the time complexity for the best case and the average case and the worst case is all the same. It's going to be on the order of n squared because you've got two for loops. They're nested. So the outside one is going to be responsible for going through roughly n times. The inner one also n times. So there's where we get the n squared. We're going to take that process even if everything's in order, which would be our best case. We're still going to have to go through all the mechanism steps. And that's why the best case and the worst case is identical, because there's no savings if we have a ordered array already. In terms of space complexity, we're going to pretty much sort in space. We're not going to need a whole lot of extra space except for one temporary variable. Therefore, we would say it's on the order of a uniform space complexity. So that was the selection sort. So let's take a look now in section 19.7 at insertion sort. Insertion sort works a little bit differently. It's a sorting algorithm that takes it into two parts. You've got a sorted part and an unsorted part. And it repeatedly inserts the next value from the unsorted part into the correct location from the sorted part. So unlike starting with the leftmost and moving to the right, we start with two different portions, and we have one that we know is in order and the other one which is a jumble, and we just take one at a time and sort it. This may be as similar to approach you would take if you had a bunch of numbers on cards on a table and you knew that you had some that were sorted. I typically do this when I've got last names in homework assignments. I may take some and then I'm grabbing one from the unsorted pile and putting in the order in the sorted pile so that I have all the last names in order. Let's take a look at this example. So initially we have I and J equal to each other. So we start with the sorted part, which is just a single number. We're going to assume that's sorted. And then we have four numbers that are not sorted. What we do is, while we're not at the end, what we're going to do is we're going to take that and say, okay, look, the one that we have, the first one we encountered, should be at the beginning of the sorted pile. So that's why we move it to the beginning. Next, we go through it again. We move our I and J over, and we say, is 15 less than 32? And now we're going to have to compare that 15 against 6, because the sorted pile, we don't know where that number is going to go. But we do know that 15 goes before 32 and after 6. So the sorted pile is going to have those two in order. And then we just keep going over. And just like this, we have values that are following a set order. Now we have 3 and 32. So now we see where 3 goes. We keep moving it over and making comparisons until we find its place in the sorted list. In this case, it happens to be in the beginning, so we're going to have comparisons to move the 3 over. Now, we have our list pretty much sorted all the way over to 32. So now we take 20, we just need to find its place in the sorted list. It's our last remaining unsorted number. And so once we come by going in decreasing order, we can find its place in the list. So let's do a comparison and look at like big O notation. So we have a for loop and we have a while loop. Let's take a look at the algorithm in BlueGene. Again, we have our unsorted and sorted list. This is what we're going to print out. So let's go through it. So we have I, j, and temp. So initially we have this for loop. We're just going to loop through all the numbers from 1 through the length of the numbers. So we're going to make sure we have our list. Initially, we're going to set j equal to I, because that's our starting point. And then we're going to do a while. And let's take a look and see where this while goes. It goes from as long as j is greater than 0 and numbers j is less than numbers j minus 1. Let's take a look at this while statement. So it's going to keep true while j is greater than 0 and numbers sub j is less than numbers j minus 1. So that's where we're doing the shift. So we need a temporary value for the swap, and as long as we keep moving down through the sorted space to find the location of the number, that's what's going to tell us when to stop. Let's compile and run this. And just like previously, we get the same unsorted list that's sorted. It happens so fast that we can't really see the time difference, but let's take a look and see how the insertion sort stacks up. At first glance, it looks like the selection sort and insertion sort look very similar. However, look at the best case, which is when we're starting with a sorted list already. In that case, it's going to be much faster because the while statement is not going to have to do much. We have the outside for loop that's going to have to loop through once, so that's where we get the order of n. However, if everything's sorted, we don't have to do much in terms of our while statement. And in that case, it's really going to save us some time. And that's why, in the best case, the insertion sort is better than the selection sort. All other things remain the same, including space complexity. Here's an example showing why it's order n. Here we have a list that's fairly close to being ordered. So what we're going to do is we're going to go through and take the unsorted list, and we're not doing a whole lot here. We don't have to move a lot of values. In fact, the only value we have to move is here towards the end. So you can see it's going to be a faster algorithm than with the selection sort. Makes one more comparison. And there we go. We didn't have to do a whole lot of moving like we did with the selection sort. Now let's take a look at the quick sort. So quick sort, like its name, is one that repeatedly partitions the input into low and high parts. Each part is unsorted. So unlike what we just saw with the insertion sort, here we have two unsorted parts, and we're kind of breaking the problem into two and working on each part independently, and then we have a pivot. So what the pivot is any value within the array, which we start with the middle. And if you remember what we did with the search, when we had the binary search, it's kind of its counterpart here. Let's take a look at the quick sort and see how it works. Initially, what we have to do is we have to calculate the midpoint. The midpoint is the middle point in our entire array here of 5 elements. In this case, it happens to be 2 because we start counting at 0 and our last one is 4. It happens to be the third element over. Taking the value inside, that happens to be 6. So that's the value of the middle element. So index L begins at element I and is incremented until a value greater than the pivot is found. And so now we found our value greater than the pivot, which happens to be in L. And then we also do the same thing with H. We begin with element K, and it's decremented until a value less than the pivot is found. So we're working both ends. Now the elements at indices L and H are swapped, moving those elements to the correct partitions. So that's why we swap the 6 and the 7 here. Now the keeps repeating itself until L and H reach or pass each other. So remember, we're working our way inward. So that tells us whether we've partitioned everything correctly. And now once everything's been partitioned, the algorithm returns an H, which indicates the highest index of the low partition. So that in our case, the highest index is going to be 4. And the index itself is 1. Now keep in mind, we haven't yet sorted the index, we've just partitioned it. You can see how we've done it. We have a low partition with elements 0 and 1, and then we have a high partition with elements 2, 3, and 4. So now let's take a look and see how this is done. So the list contains more than one element, so we have to partition our list. Remember, we had this low partition and the high partition from the last exercise. Now we recursively call quicksort and on the high and low partitions. So you can see here we're working in the code with two different calls, one I and J, and then the other one's J plus 1 and K. So these are two separate calls. It's kind of hard to illustrate this, so let's take a look at one side. So the low partition contains more than one element. You see 2 there. So then we have to partition the low side more than once and call quicksort. Once again, now we have one element, so we can say that that partition is already sorted. The high part of that, which is the value 6, is already sorted as well because it only contains one element. So keep in mind this is recursive. So we put things on the stack and we pop them off. So now what's going on is the high partition contains more than one element. It's got 3. So we partition the high into 2 separate, both high and low. And then we recursively call quicksort again. And just like we did with the low side, we're going to do the same thing to the high side. We're going to split it up once again. And when we split it up once again, now we have everything that's got a single element. So now we can say that every single partition is sorted. So in step 7 here, what's happening is the low partition contains one element. And so we've got a completely sorted algorithm. This is just our check. And now because we've got everything sorted, we say, okay, everything's in order. So although we have only 5 elements, each part of its own partition, each having one element, we can say that every partition here. Now we begin the third step. The third step is to put them back in order. So if you look at the order here, we have 4, 6, 7, 8, and 18. It's quite easy to put those back in order. Let's take a look at the code. So you can see with quicksort, things get a little bit more complicated just because we have more pointers. What I consider pointers are the L, H, midpoint, pivot value. So those are the values that we have to keep track of and that they're constantly changing. This is something that you might see on an exam when you go to an employer. They might ask you to explain a quicksort or explain the difference between these different sorting mechanisms. Very, very common question for an introductory software engineering position. So it is important for you to kind of understand what's going on. What we're doing is we're doing the sort and we're comparing the sides one by one, start with low and high. And you can see here we're making comparisons. But what's interesting here is you have these recursive calls here. So we have recursive calls in quicksort. So this whole method here is calling itself multiple times, each with smaller values. So each time we go through it, we're splitting the numbers into low and high in smaller and smaller increments until we get a single value. And that's when we know to stop. Let's go ahead and compile it and run it. And just like the previous one, it works fast. Now let's analyze the complexity. So quicksort is a much more efficient algorithm overall. And the reason we know that is in the worst case, it doesn't really save us a whole lot. You can see here with insertion sort and selection sort, the worst case is we go through the loops twice. However, with recursion, the first time through, we're going through all the elements. But the second time through, we're actually saving, we're going down and we're reducing. And that's what recursion does, is it allows us to save this because we're partitioning smaller and smaller sizes on either side. So not only if we start with a sorted list, are we going to get n log n, but also the average complexity, which is typically the more interesting metric to evaluate, is n log n as well. So if we go down here and look at insertion sort, we had, of course, selection sort had the worst. It doesn't improve regardless of whether we have a sorted list or not. However, insertion sort gave us a little bit of a benefit if we had an ordered list or a nearly sorted list. Actually, insertion sort in the best case, which is a sorted list, actually outperforms the quicksort. However, the average case, which is typically the metric we're most interested in, it's going to perform better than the insertion sort because n log n is going to be a smaller number on average for the number of elements than it is for n squared. Look at our space complexity. We have a lot of sorting. So instead of having a uniform space complexity, it's linear. And that is because we have to maintain a different component of the list. So if we have 10 elements, it's going to be 10 times as needy for space than it is for the insertion or the selection sort. Now let's take a look at our fourth sorting algorithm, merge sort. So merge sort is one that divides the list into two halves and then recursively sorts each one and then merges them together. So it would be like if you had a bunch of cards to sort in order and you take half and you give your friend half. You each sort your list and then you combine the two lists together. Of course, this looks like it's not going to be very efficient because that last merge is going to be a little bit difficult. But if you think about it, if you know these two lists are sorted, you only have to compare a few cards in each pile before you know you can sort. Let's visualize this. So initially what we're doing is we have to determine the size of our arrays. In this case, we start with 6 just to make it easier for illustration. So we start and we divide our lists into 2. Now we are dividing it again. Then we divide it once again. We do the same thing with the other side. So now we know we've got each list sorted. So we've got 6 different partitions. And now comes the merge part. So now we need to start merging these back together. Let's take a look and see how this works. So with the merge sort, we need to partition these 6 elements into 2 separate lists. And we try to do it as evenly as possible. So we have 3 and 3. What we're going to do is we're going to recursively call these methods until we get everything partitioned into, in our case, 6 different lists, each with 1 element. Once we get these 6, we know that each of them are already sorted. And now, because we've got sorted lists, we're going to take and merge them. Okay, so we do this on each side. So now we've got these sorted lists. So now it's pretty easy to put them in order. Because if I have 3, and I know my next card's 8, I can put the 3 here, and then I can just go to the next value that's higher than 8, which happens to be 18, and I know where to insert the next card. So it's relatively quick. Let's take a look at this list and how we do the sort itself. Again, this explains how we take these lists and we merge them together. Much like you have a set of cards, your friend has a set of cards, and we're trying to figure out where do we put them, either in a single pile or your friend gives you one card at a time. Because one list is sorted, you don't have to sort through the whole list. You just have to find the next one that's greater than or less than. And you just repeat this again and again. So with 11, because I've already done 4, I just have to compare it against 18. And then I'm done with my list, so I know the other numbers just go in place and they make them. So because that portion's already sorted, they just make their way up there. In fact, you can do both at a time because you know you've got a sorted portion of the list. Now we've got our list. Let's take a look at this in BlueJ. So again, we're going to make this call recursively. We're going to call it multiple times until we get partitions of single values. So we keep track of the position in the array. This is kind of an index, and we have a way to find the position. And again, we keep moving it and making comparisons. Here we've got a while loop with if else, and then we have a second while statement, a third one, and now we have our for loop. And remember, what we're doing is we're going to call merge sort for each side. And remember, we're getting the list smaller until they have a single value, which means we have partitions of. Let's compile and run this. And just as we suspect, it gets everything in the right order. Of course, if we had a really, really, really long list of numbers, we would be able to see the performance difference. That might be an interesting aspect of a project. If you had a way of timing and you made some sorts of different values and you ran it multiple times, you could take a look at the performance of each. Let's take a look at how merge sort compares to the other 3 algorithms for sorting that we've looked at. The nice thing is it has not the worst but not the best time complexity for the best case, in other words, a sorted list. Not any better than quicksort, but it's certainly not as bad as selection sort, and it's a little worse than insertion sort. Now let's take a look at the average case. The average case is going to be the same as the quicksort. So it's going to be better than the insertion sort and the selection sort. Now the worst case is where it differs from the quicksort. So in the worst case, quicksort is going to be on the order of n squared, whereas merge sort is going to be very consistent, whether you have the best, the average, or the worst case. However, with space complexity, it's going to share the need for additional space because you are partitioning values and you have to keep track of those values as opposed to just having a single temp value like we had with the insertion sort and the selection sort. So which of these 4 sorting algorithms are best? Looking at average time complexity, I would say the quicksort or the merge sort are probably going to be your better overall in the average case. However, sometimes we want to look at the worst case too, because that might be the one that is going to annoy people. If we're trying to save time, the merge sort might be the best one, because it's the only one that's less than order n squared. If space is your consideration, the insertion and selection sort would be a better option. I hope this gives you a primer for what you'll see in CS 301. You'll be talking about these types of algorithms in more detail. Please try these algorithms out. I'll provide them for you inside of Canvas. And if you have any questions, please reach out to me. There's many resources also online. Thanks.